Okay, so what's the convergence property of the Jacobi iterations? It's actually the way to analyze convergence, although the meaning of convergence is very different. The way to analyze it is actually very similar. This is the solution satisfied by the true solution. This is the equation satisfied by the still converging solution. So let's subtract them to get an equation for the error. Ek, let's define it as xk plus 1 minus the true x. Okay? Very similar to what we did before in convergence analysis of finite difference, right? We did all the stability and analysis by subtracting the numerical solution from the true analytical solution. Here we subtract the still convergent solution from the actual numerical solution. So now we subtract them. We get d times ek plus 1 is equal to minus a minus d times e of k, and the f's cancel. Okay? Or if I invert the d on both sides, we get ek plus 1 equal to minus d inverse a minus d times ek. So now this equation determines how each successive iterations are going to decrease in the approximation error. Okay, and this particular matrix minus d inverse times a minus d is called the iteration matrix of Jacobi iterations. Okay, now let's actually just compute what that matrix is and look at its eigenvalues to see how it converges. So we have minus d diag of, okay, so let's say d equal to diag of a. Right, so basically if you do diag of a, it just extracts the diagonal entries as a vector, then you have to diag it again to actually make it a diagonal matrix. So then the Jacobi iteration matrix, let's call it J, is actually equal to minus d backslash, inverse of d is basically backslash a minus d. Right, so that's my Jacobi iteration matrix J. And if you look at it, it's basically, I have 0 on the diagonals, which is actually a property of all Jacobi iteration matrices. It has to be 0 on the diagonals. And in this particular case, we have half and half on its neighbors. Okay, so what the matrix is doing, if you think of how you multiply the matrix with a vector, is that for every grid point, I'm just taking the average of 2 neighboring grid points. Right, this matrix is applied to the error, right? So basically at every iteration, after every iteration, the solution error or the iteration error of one grid point becomes the average of the iteration errors of the 2 neighboring grid points. And now what's the eigenvalue of such a matrix? That's exactly what we are talking about, right? So it maps the eigenvalues of the matrix A from whatever it is to minus 1 and 1. All right. Just the reason the solution was converging so slowly is because 2 reasons. One is that the smallest one is really close to -1, and the largest one is really close to 1. Right. Yeah. But like despite the slow convergence, this is actually a much better way of solving large linear systems, especially when deriving from large 3-dimensional systems. So for example, let's just think about how many iterations we have done to actually get to a pretty good solution. We have done like 300 or 3,000 iterations and then a 10,000 afterwards, right? So we did something like 13,000 iterations to get to there. But each iteration just involves an order operations that is basically proportional to the number of grid points. And suppose we are not having 100 grid points just in one spatial dimension, but in all 3 spatial dimensions, which makes our system size about 1 million, right? Is that right? Yeah, I think so. It's about 1 million grid points. So for 1 million grid points, if you solve using direct method, the cost is 1 million cubed. While if you use iterative method, by the way, even if you have 3 dimensions, the eigenvalues are about the same as this one. So the convergence rate is roughly the same. It's actually a factor of 3 times slower if you are in 3 dimensions. So not much smaller than this. Instead of 13,000 iterations, maybe we are doing 36,000 iterations, right? But 36,000 iterations, each with about the order of 1 million operations, is much cheaper than the order of 1 million cubed operations. Okay, so this is why the iterative method is particularly popular when you are solving actually truly 3-dimensional problems. When you are solving, for example, very large 1-dimensional problem, maybe not that much, because for example, for Poisson's equation and Poisson-like equation, the more grid points you have, the closer the largest one and smallest one is to positive one and negative one, making your convergence even slower. All right.